This video is about descriptive statistics using Microsoft Excel. Descriptive statistics is one important type of different type of analytics help us to make sense of data. And one of the key feature of descriptive statistics is that they are based on past data. That can be considered their limitation and also an advantage. Limitation in the sense that because they are based on past data, so anything that we are going to develop will be reflective of that past performance. But it's also an advantage because that past data helps us to define a trend or to understand a trend where the process would be going in the future. There are 5 categories depending upon what's our objective. These descriptive statistics, they can be used to create a distribution from data, and relevant statistical tests would include histogram, skewness, and kurtosis, or measure of location, for instance mean, median, mode, and geometric mean. Measure of variability, how much is dispersion in data, and a relevant test would include range, standard deviation, and variance. And then analyzing distributions in terms of percentiles, quartiles, z-score, and box plot. And the last category would be association between variables using scatter plot or correlation. We will start with the first one, creating distribution from data. For this purpose, we'll be using this data that's called as height weight, which means we have a sample of height of people and corresponding weight. But first of all, a very brief idea of histogram. Histogram describes the shape of data. If I select this data, again you can just click the top value and then press Ctrl Shift lower arrow key, and the whole column will be selected, and then click on insert and then histogram. Now we'll be discussing this histogram, but let's do a little bit labeling. First of all, chart title, I will write here histogram of weight. Let's also add here x-axis label, and for x-axis label, if you are using a MacBook, then you will click here on the top left where is add chart elements and axis title primary horizontal, and primary horizontal I will add here weight. And if you are using Windows, then when you select or click this chart histogram, then here on the top of this chart there will be a plus sign. If you click that plus sign, then you will have a number of options, and from that options you can choose axis titles. We can experiment with this one in terms of number of bins. So these are bins. This one has 1 2 3 4 5 6 bins. If you are using MacBook and you want to refine this histogram in terms of number of bins and the width of these bins, then double click this area, or double click any bin, and then you will have here bins. So by default it will be on auto, but you can always change. For instance, let's say number of bins. If you want to change number of bins, it says right now we have 6 bins. These are 6, 1 2 3 4 5 6, and we can change to 8 or 10. So let's say for instance when I do it 8, it gives me this one. Similarly, width of bin, it can also be adjusted. Right now bin width is 6 and I can change it to 5. The next step is, how do we interpret this histogram? What is the utility of this one? They help us to understand a process. So a normal histogram should have been like this, but our histogram is not like that, which means one thing is that there are some extreme values here in this region. These are some extreme values which are creating a tail. Second thing is that our histogram, there are also some values here which are creating a spike. This spike is measured in terms of kurtosis, and the symmetry of a histogram is measured in terms of skewness. A normal histogram would be like this one, but if a histogram is not like this one, and if you have large data and still you don't get a histogram like the one in green color, it means your data is telling you something. As you can see here, here's a tail, and which means a normal one should have been like this one, but here's a tail, and this tail has meanings, and we call it skewness. And because it's on the right side of histogram, we call it a right skew or positive skew. This tail can also exist on the left side, and then we call it left skew or negative skew. But in this case, where we have this tail on the right side, one information that this skewness tells us is that there are some outliers, possibly some outliers. Second thing is that there are some values, although most of values they are on the left side, which is normal, but these values on the right side, they are creating a tail. Third information is that's about median. In a normal histogram, this should be median, which means the central value. But in this case, because there are some values which are larger values and they exist in data, so therefore they will drag the mean of this distribution to somewhere here. The mean is typically greater than median, and the majority of data points are concentrated on the left side, and those that are on the right side, they will create a tail, and that tail is on the right side. Now here is an example. As you can see here on the left side, we will call it left skewed, and we call it moderately left skewed, which means there are very small values that are causing this tail, so we call it left skew. And this one here, we have some large values and they cause this tail, we call it right skew. This one appears to be very symmetric, and this one is highly skewed on the right side. There are two ways to make sense of this one. One thing is visual, which means just by making histogram, and the other one is quantitative, number that can tell us if there's a skew. And for that purpose, here's a function in Microsoft. If I write here is equal to skew and I select this whole column, now it says that skew is 1.05. Normally this skew value should be between -1 and +1. If it is less than 1, it means there would be a skew on the left side. If it's greater than 1, it means there would be a skew on the right side. A symmetrical data would have skewness that's close to 0. And we know because in this case, we have here a skewness that's a positive skew or right skew. Therefore, having this value that's 1.05, it makes sense. Now I will give you some examples of data where right skew and left skew are perfectly normal and you can expect it. Now for example, time to failure cannot be less than 0. Then wait and response time cannot be 0, cannot be less than 0, but there are no upper limits. Same thing also applies to sales data. Sales data cannot be less than 0 and there is no upper limit. So therefore, in that case, we can expect there would be a right skew on the right side. Similarly, humans have a minimum viable weight, but there is no upper limit to extreme values, and extreme values always exist. And these extreme values, they will create a tail. And last thing for right skew is income of people. If there are millionaires and billionaires, they would create this right skew. Similarly, left skew, which means a tail on the left side, is also possible in many situations. For instance, we know purity cannot exceed 100%, but on the lower side, there can be a range of values, and that will create a tail on the left side. Maximum test scores cannot exceed 100%, but on the other hand, people can have very low scores and there can be a range of values on the lower side. So that will create a tail on the left side. Then similarly, ages of people, average age of people is 70 to 80 years. Extreme values are more likely to appear on the lower end. Then the next thing in examining a histogram or a distribution curve is called as kurtosis. Kurtosis is a statistical measure used to describe the degree to which scores cluster in the tail or the peak of a distribution curve. And for this purpose, again, we will be using the same data, that's height and weight. We look at this one. Again, a normal histogram should be like this, but we know it is not like that. First of all, it has a tail that we have already discussed in terms of skewness. It also has this spike, and this is something that relates to kurtosis topic. Normally it should not be there, but it is there. There are three types. One thing is leptokurtic. Leptokurtic means when histogram is bit thin, lean, tall and slender. So this one is leptokurtic. Orange type histogram would be called as platykurtic, which means as if it has been hammered from the top. That's called as platykurtic. And a normal one, the green one, would be called as mesokurtic. And we can also determine this by having a numerical value. I will write here kurt and I will select this whole data. Now that kurtosis is very close to 1.14. Now normally we would say that this kurtosis should be close to 0. If it's close to 0, then it means it's a perfect one. If it's positive, as we can see here, it's 1.14, then it means it's a leptokurtic. And we can also see it's clear from the histogram as well. And if it is negative, it's platykurtic. The next thing is arithmetic mean. Arithmetic mean is used to calculate average. Let's say top 20 car sales, and we have this sales, and if I want to calculate average in the month of February, so that average turns out to be something 12,705. But this average or arithmetic mean, although it has certain advantages because it's very intuitive, it's very quick, and it's very frequently used, but it also has certain limitations. One of the limitations is that arithmetic mean is very sensitive to changes. If we have some negative values, then arithmetic mean could be very distorted. So for instance, I will do it here. Let's say if I take average of 10 and 8, I can imagine it would be 9. 10 plus 8 is 18. 18 divided by 2 is equal to 9. But on the other hand, if I take average of negative 10 and 8, now this will be significantly different, and it turns out to be negative 1. Now many times we are not interested in this negative value, and we do not want it to be considered in our calculation, because many times this negative value is only telling us about the direction, that if something is going up, going down. We are not interested in that negative sign, we are only interested in the absolute value. But arithmetic mean would factor in that negative sign, and it will create a distorted 1. So you see here, this is 9 and this is negative 1. So arithmetic mean is very sensitive to this one, and therefore sometime we do not prefer arithmetic mean. Then the next one is median. Median is about the middle value. Now for example, let's say if I have this data and we take its median. Median is this one. Median has many applications in business, and one of the biggest advantage of median is that it's quite stable. First application of median is in house prices. Whenever you want to buy some property, you are interested in what is the median price, although you can also use arithmetic mean. But one of the limitation of arithmetic mean is that if there are some very expensive houses in that area, they will distort that mean, and you won't be getting a good idea of real estate prices. Therefore you want to know the median one, because median it's not affected by those outliers. Median is a good indicator of house value. And similarly, when we use SAT score or other educational purposes, and we want to separate out the top 50% from the bottom 50%, we use median. Mode is the value of observations that occur most frequently. So for instance, if we have this data, in this data you can see there are some values that occur more than once. For instance, 13 appears 2 times, 14 appears 3 times, 15 appears 3 times, and like that. We use mode because we want to see which values occur most frequently in our data. And for this purpose we use this command, that's mode multi, M-U-L-T, and then select this whole data. 14, 15, 17, 18, 20, 22 and 33 appear more than once in this data, and we want to refine this information. I want to see how many times 14 appears, 15 appear, and for that purpose I will use COUNTIF function. So COUNTIF is select this range, and in this range I want to find out 14 appears how many times. and if I hit enter, it gives me 3, and then I can drag it down. It says that all these values 14, 15, 17 and all these values, they appear 3 times. Now there are different types of modes. There is a possibility that a data does not has a mode. For instance, in this case 1, 2, 3, 4, 6, 8, 9. None of the values appear more than once, so therefore this data does not has any mode. Then there could be just one mode, that's called unimodal. For example, in this case 3 appears 2 times. Bimodal, which means there are 2 modes. For example, here 1 and 1 and 4 and 4, and then 3 trimodal, etc. Now the next thing is geometric mean. Geometric mean is a very useful mean that's used in finance and in investment related decisions. But let me first explain it with an example. Just imagine you have this rectangular prism, and in a rectangular prism length is greater than width or height, and suppose that you are asked convert this rectangular prism that's made of Play-Doh or any other soft material into a cube. How would you do that? Now considering that this rectangular prism is made of Play-Doh, so which means you can compress it from sides, and you have to compress it in a way that the extra length is distributed equally, so that at the end of the day length, width and height, they are all the same, and that becomes a cube. So if we could do that, that would be called as geometric mean, which means we have distributed it equally. So for instance, let's say we have here 4, 7 and 12.25, and if I take geometric mean, I would say is equal to so if I take geometric mean, that's 4, 7 and 12.25, these are the dimensions that have been given here, then geometric mean will be equal to 7, which means that we have to reduce this side to 7, width should also be 7 and height should also be 7, and in that case it will be converted into a cube. Difference between geometric mean and arithmetic mean is that arithmetic mean finds the center by summing the values, while the geometric mean finds the center by multiplication. Now I will give you an example here. Just imagine you started a new job and your salary is 100,000, and in the first year you receive 5% raise, and in the second year because of learning curve you get a raise of 15%. In the first year your raise was 5%, and in the second year your raise was 15%. And at the end of the second year, if someone asks you how much was your average raise, you will have a tendency to say, okay, I will take arithmetic mean of 5 and 15, which means 5 plus 15 is equal to 20. 20 divided by 2 is 10. So you would say that my average raise is 10%, but actually that would be wrong. Your actual raise is 9.886, not 10%. Now I will explain this here. So for instance, here is your salary, starting salary 100,000. Now in the first year you get a raise of 5%, so raise will be equal to 100,000 times 0.05, which means 5%, and which means your raise for the first year was $5,000, and then your salary becomes 100,000 plus this raise, so which means by the end of the first year your salary will be 105,000, and for the second year your starting salary will be 105,000. This year raise is 15%, so this number multiplied by 0.15, which is 15%, so your raise increase in salary will be 15,750, and your total salary or revised salary by the end of the second year will become 120,750. So that will be your salary. Now I'm going to using arithmetic calculation. Now your raise will become your starting salary and multiplied by 10%, and your salary at the end of first year will be 110,000. Okay, and this 110,000 becomes your starting salary for the second year, and then again you have the same raise, that's 10%, so this multiplied by 10%, and then at the end of the second year your salary should be 121,000 according to arithmetic mean, but we know that your actual salary was 120,750, which is different from here. So one of them is wrong. Of course, this arithmetic mean is wrong. In order to address this limitation, we can use geometric mean. And for geometric mean, I will do it here. Now this is how we get geometric mean. You start with 5 and 15 percentage and make sure they are converted into percentage. And this is how I will click here. I will use this formula that gives us geometric mean, that's 9.89%. So it says that geometric mean will be 9.89%. Okay, let's use this one. The starting salary is 100,000 and raise is equal to this one multiplied by 9.89. so this is the raise, which means 9,886, and revised salary will be starting salary plus raise, and this salary it becomes starting salary for the next year. And here we have again a salary at the start of the second year multiplied by 9.89. and now you see here, when we use geometric mean, then revised salary turns out to be 120,750, which is actually the correct one, which is actually what we calculated manually. So this is how geometric mean is different. I will repeat this point. When we are calculating salary and we calculated manually, your final salary turns out to be 120,750. If we use arithmetic mean that we did here, it says that your salary should be 121,000, which is wrong. However, when we use geometric mean, it will be 9.89%. It gives us exactly the correct one. There is another way to do that. So for instance, over here we knew about this one, geometric mean. There could be another situation when you want to know how much my salary increased, percentage change that happens. I will use power function, power of last value and first value. Last value is this one divided by first value, that's 100,000, and then comma 1 over number of periods. There are 2 periods, we are talking about 2 years, and then minus 1, it will become 9.89. Measures of variability. And there are 3 things: range, standard deviation, and variance. Range is basically the difference between the highest value and the lowest value. So for example, if we use home sale data, this is home sale data, and in home sale data, this is selling price, and then standard deviation. For standard deviation, I will just write here STDEV, that's the abbreviation of standard deviation, and selecting these values, and we get this one. The standard deviation means how much variation exists among these values. So we can say that this variation in house price is 95,000. If there's a greater standard deviation in some data, it means there is more spread in data. But if standard deviation is less, it means data values are clustered closely. Now those people who work in manufacturing organizations, for them standard deviation is very important, because they need to control quality of the product. And if standard deviation is very high, it means all the products they are making vary significantly, which is not desirable. So therefore they want to reduce the standard deviation because they want all products to be of the same quality. So standard deviation will tell them, are they doing good or wrong? And then minimum, it will tell us the minimum value, the house that was sold at the lowest price, it is this one, and maximum is, the maximum value is this one. Now the range will be the difference of these two. Let's say calculate range, the difference of this one, and then there is another thing that's called as variance. It's not very much intuitive, and if you take square root of this one, it will give you standard deviation, this one. So as you can see here, if I take square root of variance, it should give me standard deviation. So you see this number and standard deviation, they are identical. In analyzing distributions category, we have percentiles, quartiles, z-scores, and box plot. So first is quartile. The idea of quartile is that we divide the whole data into 4 parts. Quartiles divide a set of observations into 4 equal parts. The first quartile labeled as Q1, and then it contains 25% values of the total. And then we have second quartile, and that contains up to 50% values, and that's also called as the median value. And third quartile is Q3. Sometimes rather than dividing data into 4 parts, we can also divide it into 10 parts, and that is called as deciles. But quartiles are more common and percentiles are more common, and in percentiles we divide the whole data into 100 equal parts. So for instance, let's say we have this data. I will use the syntax quartile, and I will select whole data, and then you need to write 1, which means that it's a first quartile, and then it says first quartile is 24. Second quartile will be again selecting whole data, and then 2, which means that second quartile. Similarly, third quartile will be whole data, comma 3, and last one will be quartile, whole data, and 4. So these are 4 quartiles. We also call them Q1. For percentiles, we use this formula. Let's say 10th percentile, and that will be equal to percentile, again selecting the whole data, and then for 10% we'll write 0.1. 0.1 means 10%, and this gives us a 10th percentile, that's 23. Similarly, if we want to get 70th percentile, that will be equal to percentile, selecting whole data, and then 0.7. For percentile, this is 10th percentile, 23, which means 10% of values they fall below 23, and 70th percentile is 34, which means about 70% values they fall below 34. SAT scores or other scores are described in terms of percentile. If someone has a score of 90th percentile, that would mean 90% of students score less than that particular student. The next topic is z-score. Z-score is used to make sense of data and to find out outliers. It is used to measure the relative location of a value in a data set. It helps to determine how far a particular value is from the mean relative to the data's standard deviation, and it's also called as standardized values. Now for this one, let's use this data that's TreadVS. Let's say we just pick up one variable, miles. This requires mean and standard deviation. So let's first calculate mean and standard deviation. So mean and standard deviation have already been calculated here. To calculate standardized, miles is equal to standardize, and then you see in suggestion it shows x value, which means this value, miles, and then mean is given at the bottom. So when you select mean, make sure you also press F4 key to lock it, to make it absolute, because in the next step we'll be dragging this thing, so we want to lock this value so that it doesn't change. Standard deviation, and standard deviation is also again given at the bottom of the column. Here is that if I drag it down, I have all these values here. The utility of this is that we use this one to find out outliers, if any. If I choose from the filter value ascending, which means lowest value comes at the top and then other values they keep increasing gradually. So this is the lowest value, and you can see here lowest value is minus 1.07. What about highest value at the top? The highest value is 3.47. Now the rule is that 3 standard deviation on either side. If I draw it, I would say if this is a histogram and this is mean value, we would say 1 sigma, 2 sigma, and 3 sigma. And similarly 1 sigma, minus 1 sigma, minus 2 sigma, and minus 3 sigma. And this is the mean point. Empirical rule which says that when you have a large sample, then all values, they will fall within 3 sigma from here and 3 sigma from here. And there are some values that are greater than 3 sigma. These scores, they are greater than 3, which means they do not match with other data. Now for example, if we look at this one, and you can see here that these values which are greater than 3, they represent miles which are in 6 digits compared to other one that are just in 5 digits. So we can consider them as outliers, or these are tires that went extra long. Similarly, if we want to see on the lower side, the lowest value is minus 1.07, and the rule is that it should be between plus 3 and minus 3. We don't have any problem on the lower side. The empirical rule says for a bell-shaped distribution, approximately 68% of the data values fall within one standard deviation. So for instance, let's say here we have this one, this is our mean. If this is one standard deviation and this is one standard deviation, this one represents 34%, this is 34%, this is also 34%. So 34 and 34, that will be 68%. Approximately 68% of data values fall within one standard deviation, which means plus 1 and minus 1. Similarly, okay, if this is plus 2 standard deviation and this is negative 2 standard deviation, it says 95% of data will fall between this point and this point, which means everything here, that will be 95%. And almost all data values, they fall within 3 standard deviations. The next thing is called as box plot, and for box plot we'll be using this home sale data. So we have this home sale data. So box plot is a chart. To make box plot, so first we need to select this data, and after selecting data, if you're using Windows and when you click on recommended chart, then a box plot would appear here and then you click on that. But if you're using MacBook, you can just click on this scatter plot, and once scatter plot is there, then click here and right click and then change chart type, and then in statistical category you will find here box and whisker plot. Now let's format it a little bit. Let me call it box and whisker plot, and let's add more information to this one. Add data labels. Let's try. We can add data labels, or if you believe it makes it cluttered, you can remove it. Format data series, and in format data series show inner points. I don't think we need it. It makes a chart very cluttered. Show outlier points. Yes, we need them. Show mean line. Now this is the minimum value, and this line is called as Q1. So which means 141,000 will be Q1, which means 25% of values in this data set, they fall below this point. And then we have this Q2, that's median, which means 203,750, that represents the median point. And similarly, this represents Q3, which means it represents up to 75% values. And this is maximum non-outlier value, and this is an outlier. So one of the advantage of box and whisker plot is that it helps us identify outliers. So this is an outlier, which means it is not congruent with the rest of the data, so therefore it will be considered as an outlier. Another benefit of box and whisker plot is that it also helps us to identify skewness in data. So this figure, it shows there's a long whisker here. This whisker, the upper whisker, is longer than the lower whisker, and because the upper whisker, it represents higher value, which means if we make a histogram of this data, that will be right skewed or positive skewed. Similarly, in this one, the lower whisker is long compared to upper whisker, which means those values that are smaller, there are some small values that can be considered as outlier, they are there. So which means this one will be left skewed or negative skewed. Let's do one more example. Treadwear data. We want to make a box plot of miles. So I will select this whole column and then click on insert. Box plot option is not there, so I will click on scatter plot, and once I have scatter plot, then I will right click. I will change chart type to statistical and then box and whisker plot. So I have got this box and whisker plot, and as you can see here, there is a long whisker, which means if I make a histogram of this one, that will be right skewed. Insert histogram, and you can see here's a histogram. So you can see here that this histogram is right skewed or positive skewed, and the same thing is also confirmed by long whisker, which means there is a skew on the right side. The next one is measure of association between two variables. These are two tests. The purpose of them is to find out if there is a relationship between two variables. You will always have two variables. One will be independent and other will be dependent variable. Scatter chart is visual, and correlation coefficient would be a statistical test. And for this one, we'll be using data bottled water for both of them. So here is our bottled data. And in this bottled data, we have two variables. One is temperature and other is bottled water sale cases. So we want to find out if there is a correlation between them or not. For instance, if the sale of bottled water increases or decreases as temperature increases. I will select this data. Let's go to insert and scatter plot. Scatter plot is already here. So this is scatter plot. We need to refine it a little bit. This area at the bottom, there is nothing there, and I want to trim this area. Maybe I will click on this y-axis and then right click and format axis, and it says what's the minimum value. Minimum value is 0, but we see actually the lowest value is something above 20. So I can say, okay, minimum value should be 18. That start this chart from 18, and if I hit enter, you see here that no, this axis starts from 18. And now it looks much better. Now the next thing is correlation coefficient, and in correlation coefficient I will use this syntax is equal to correl, which basically means correlation, and array1, let's select this one, and then comma, other column, and if I hit enter, it says 0.93. If I convert it into percentage, it shows that correlation between these two variables is 93.25%. Now it shows that when temperature would increase, sales of bottled water would also increase accordingly, and there is a 93.25% correlation between them, which is a very strong. Now one last thing, correlation is not the same as causation. So for example, that number of people who drowned by falling into a pool, that's a red line, positively correlates with number of movies Nicolas Cage appeared in, and that's the black color line. So you can see that there is a perfect positive correlation, but we know that this is absurd. It doesn't make any sense. A number of people falling in a swimming pool and number of films Nicolas Cage appears in, there is nothing in between them. So therefore correlation does not mean causation.